Okay, welcome back, Klondike.
Thank you. So, first of all, I want to say thanks a lot to the nice organizer that reminded me I had signed up for a lightning talk when I was on the lockpicking village, and I didn't even know which time it was. So, yeah, let's talk a bit about PaTo. PaTo is one of these weird academical projects that basically tries to convert password into tokens. Trying to solve industry problems nobody cares about, like how to securely store passwords on the client side. And let's talk about password authentication first. I mean, everybody knows passwords are used everywhere. They are almost with the user always, unless you happen to have amnesia and have forgotten it. And the protocol is really simple. Like you have Cameron on one side, Sydney on the other, you send the username and the password, you verify the username and the password, and you send a response of whether the username and password are correct or not back. Passwords have plenty of issues. So usually I do this in a really nice way. Don't raise your hand if you have never, ever, ever, ever used the same password on two different sites. You see, only two people is not raising their hands. Good, 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 good. I see two are following. Everybody knows that 1234 is an amazing password that absolutely nobody has ever used it on their bags or anything like that. And passwords get leaked. So basically, the problem is that if your password gets leaked somewhere and you are using the same password somewhere else, the attacker might try to impersonate you on the other side. I was giving this talk at Kulholmsbaden a few days ago. And basically, this is basically how you can basically get free internet connection if you ever get there. That works for every single one of the cabins they had. And all I did to figure it out is just like figuring out the one cabin that was using the password. So as you can see, even if the passwords are similar, password reuse is still a problem. So let's talk a bit about the state of the art. When we want to store passwords on the client side, that could be like your mobile phone or this computer here, you want to use symmetric encryption, maybe, with a password manager like KeePass. I strongly recommend it, or a TPM module. I solved another of these ones problems that nobody cared about, basically how to move the hash to the client side. So clip-a-hash is my own research. And that's basically how you store the password hash. Or you could use sharp partitioning, where you have various servers and you try to distribute parts of the password among the servers and then recover it. But then attackers might basically get into your computer, typical APT stuff, compromise your client. They have, obviously, this dictionary that has only one entry, and it happens to be your password, so they will always get it right on the first time, right? And they will see the password exactly as you use it on the client, so in the same state that it is before you send it to the server. So what this means is that if you are using encryption, like KeePass, they still will be able to see when you send the password to the browser in order to use it. If you are using, as I was mentioning earlier, server partitioning, you still need to connect to the different servers and ask them to send you back the different shares so you can recover the final password. If you are using hash storage, yesterday we have an amazing talk on IBM systems that said you can do pass the hash. So as you can see, these kind of attackers basically can break everything. And they can do lateral movement, they can do cross-service impersonation, and a lot of other bad things. So I started researching on this thing called PaTo. This looks like basically you generate a public key and a private key. You send the public key to the client. The client encrypts the password with the public key. And then whenever you need to do an authentication flow, you recover the encrypted key that is sent to the client, is decrypted, is verified, and then the response is sent back. So as you can see, raise your hand. Has any of you ever taken a cryptography course? Do you know what is RSA? Yeah, that's basically it. Like we use something like RSA to encrypt the password, and the server decrypts it. Now is when you can say, "Boo! This is very easy. Everybody knows this could work." Well, there are many things that you need to take into account. First, correctness. Is the algorithm correct? Well, hopefully it is. If you recover a different password, then your system will not work. Second, indistinguishability. The indistinguishability means that even if you have an attacker that has a dictionary with exactly that password, and you give them an encrypted message, they still cannot figure out whether the message is that password or a different string. And third one, we have length obfuscation. So a problem with indistinguishability is that it depends on the length of the messages. Messages have to be the same length. I think I can do a simple check here. Think about the password you use the most. Does it have an odd number of characters? Raise your hand. Come on. It's impossible everybody has an even number of characters on their password unless it happens to be 8. So, but you see a little bit what I'm trying to hint, right? Like that by knowing the different lengths of the password, you still could be able to figure out which of the dictionary entries you should use and which ones you should discard. So you need to obfuscate the length of the password. And finally, you need authenticated encryption to be able to verify that the password that was encrypted is actually what was encrypted, that it was not modified or anything. So we basically propose a box algorithm that uses ephemeral Diffie-Hellman. When I originally wrote the paper, this was an amazing idea. Then there was this cryptographic fiasco with super isogenic curve Diffie-Hellman being proven completely unsecure with classic cryptography. So this still works, but it no longer provides post-quantum cryptography, unfortunately. Then you basically extract the entropy using a pretty simple hash-based algorithm. You use that to generate a key, and then you use padding and hashing, and you can see how this basically matches. Correctness is provided by using a standard cryptographic algorithm, like AES in synthetic IB mode. Indistinguishability is provided by the ephemeral Diffie-Hellman that ensures that the client generates a new key for every encryption and then discards it. Length obfuscation is provided by padding and hashing, and authenticated encryption is again provided by a SIP. There are many extensions, and I think nobody wants to hear me talk about server-side encryption. Like client-side hashing does provide length obfuscation. If you are using that, then you don't need to use any padding. Wow, what a surprise. Additional binding data basically allows you to make proper tokens where you can add things like expiration dates to the password and so on that can be verified by the server. Problem, it needs to be verified by the server. You basically can perform k-rolling by basically sending back an encrypted password and then replacing the password. And the client should replace the password only after it has used the newly encrypted password and verified it works, because otherwise you can perform a denial of service. Oh my God, so surprising, right? Like, yeah. The last thing that I have, that I don't see on my slides, is that you can actually implement this as a proxy. You could have a proxy in front of the server that keeps the private key, decrypts the password, and then sends the message with the username and password to the server, and sends back to response to the client, and then sends any further request from the client back to the server. And by doing that, basically you can use the same cryptographic flow you have already implemented on, I don't know, whatever industrial IoT system you happen to have running Windows 98. And basically the only thing you need to change is that during provisioning, you provide the hash of the password to the client instead of providing the raw text password. Finally, this is how you prove indistinguishability under chosen plaintext attack. As you can see, basically you have two messages. If the length of the messages is different, then the game is smooth. That's why you need to provide length obfuscation. And if the adversary can guess which of the two messages is encrypted, then basically it wins the challenge. So how do we prove security? It's really simple. We basically created an adversary that can win the INCPA game using an adversary that can win the PaTo game. So this return you have at the end with A1 of blah, 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 those are the parameters that are used for the PaTo protocol. So if that adversary can win the PaTo game, then you can win the INCPA game, which means that you can break the box function. So PaTo is as secure as the box function, and that's basically the whole thing. So to summarize, PaTo works without replacing server-side login because you can use a proxy in the front. You have security equal to a token as long as box is properly implemented. And you have extensions for pretty much everything. plenty of future work that I don't think anybody here cares about because this is not academia. And usually there is time for questions, but not during lightning talks. So just come by and ask me any questions you have. Thank you.